If you're coming from most languages, you're waiting for a for loop. Scheme doesn't have one. And by the end of this, you won't want it back. The trick underneath is something called a tail call. Remember factorial? Each call waits on the one nested inside it, so the work piles up on the stack. Do that a few 100,000 times in most languages, and it topples over. So let's rewrite it so nothing has to wait. This is a named let. Loop is a little function we define and call in one go, carrying an accumulator alongside n. Here's the key. Loop calls itself as the very last thing it does. Nothing is left waiting on the answer. That's a tail call, and Kaappi turns it into a plain jump. Here's the proof. Count to 1,000,000, fine. Count to 10 million, Kaappi doesn't even blink, back in about a second. In a language without tail calls, that second one is a crash. Here it's just a fast loop. Named let isn't only for counting, it builds. Walk I down from 5, consting each number onto an accumulator, and you've assembled the list 1 to 5. This carry and accumulator shape is the scheme loop you'll reach for most. It works across functions too. Even calls odd calls even, back and forth 1,000,000 times, and because every handoff is a tail call, it's still just a loop. No stack, no limit. And if you truly miss the C-style loop, do is right here, a variable, how it steps each time, and when to stop. This one sums 0 through 4 to 10, but once named let clicks, you'll barely reach for it. So there's no for loop, because there's something better underneath. Tail calls that make Recursion free. Named let to carry your state, do when you want it, and the stack stays flat, no matter how far you count. Next time, we teach Kaappi, brand new syntax of our own. Thanks for watching. Subscribe for more Kaappi.